I'm Nishad. I've been involved in reverse engineering, kernel development, that type of thing, and both offensive and defensive aspects of security, the fun stuff, for quite some time now. So that's pretty much it, really. I like partying, drinking, a lot of other things. So okay, let's kick this off. I don't want to bore you to death with my details. So okay, before we begin, I really have to do this because I've been promised that I wouldn't be going home, at least in one piece, if I don't show this to you guys, right? So thanks to my wonderful family, goes without saying. You guys rock, thanks for having us here. You guys rock, thanks for attending. Thanks to the Dynamics guys for hooking me up with all their tools and not caring when I'm ever going to pay them, so which is good. And some of the old school guys out here, big shout out to you. Right, now that all the formalities are taken care of, what I'm going to talk about today is about how our computer systems have changed over the years, and how there's this whole bunch of other computational elements that are present in our computer systems that are both accessible and independently programmable that we don't really pay a lot of attention to, especially in the contemporary security space. And I'm going to look at how much of a mess it is out there and the potential security implications of it. And if we do have time, I'm going to go through one of the real-life cases where one of these things can be used, abused, whichever you look at it, to achieve some pretty cool things. So this is the hypothesis I'm going to make. Well, not really hypothesis, really, it's fact. But so a modern computer is not one computer, but it's a system of computers with multiple CPUs, potentially multiple GPUs, and also various other computational elements integrated into the peripheral devices. So what do you reckon? You guys agree? Yes? No? Maybe? Throw some tomatoes at me? That type of thing? Okay, cool. I'm going to assume that I'm going to take the silence as a yes, as I often do. Okay. Now, one of the interesting things about this scenario is that all these computational elements, they have been evolving over the past decade or so. And like back in the day, back in the day when you get your peripheral devices, most of them were custom ASICs. And they were just basically somewhat dumb in the sense that they did what they were supposed to do and just nothing more. Because when you're designing ASICs, you don't want to put any more functionality there than you need to, for the simple reason that it's generally costly in terms of development, verification, silicon real estate, actual fabrication process, and so on and so forth, to put more functionality than what you need into the ASIC. So it just happened to be the case that a lot of these peripheral devices just did what they wanted to, like the back in the day Sound Blaster just played sound. And the hard disk controller just read data, so on and so forth. Now that has been changing a fair bit lately. I mean, the poster boy for this revolution obviously is the GPU, right? I mean, you got NVIDIA going about how the CPU is going to be relevant in the next couple of years. And AMD reckons that their vision of the future is where the CPU and GPU becomes one common animal, and everyone lives in harmony with so much computing power. So it hasn't, the GPU usage for general purpose computing hasn't really picked up as fast as the majority of GPU vendors would have liked to, but it's becoming a significant force out there. And especially in scientific computation and that type of thing, it's becoming quite significant. If you look at the general GPU landscape today, virtually all GPUs out there today is to some extent programmable in a general purpose fashion. And a lot of these GPU frameworks actually provide you the ability to write either C or C-like code. Now, the question is, what does this have to do with malware, right? I'm getting to it. I'm going to go through the GPU stuff purely as background. I won't be focusing much on the GPU stuff because it's nice, it's powerful, but it's got a lot of processing power. But at the same time, it has some very strong limitations when it comes to the kind of stuff that we want to talk about. So how does this all relate to malware? Well, simple, right? We've built a lot of infrastructure to deal with malware. Like, we got so much tech out there. I mean, we got basically cloud solutions. We got host intrusion prevention systems that hook everything that they can get their paws on. And we got all these virtualization solutions. So, I mean, the CPU is pretty well covered. So, like, for example, when I say, how low will malware go, someone might say, well, we do stuff on the CPU now. The next level might be the hypervisor, or go one up, go to the BIOS, or go one up or down, whichever you look at it. Go to something like Intel's active management technology and things like that. But to me, it's cool, but also like same old, because like we've been playing this game for a while. You had user land, so we went kernel and then they went kernel, we went hypervisor, and then they go hypervisor, we go AMT. So, I mean, it's all in the CPU space. We have a lot of tools to deal with this type of thing, and there's a lot of infrastructure built. There's a lot of analysis engines out there, and malware. There's a ton of malware analysts who are totally comfortable looking at these things. So what I'm going to be talking about today is to take into consideration the fact that the modern computer systems have a lot more programmable, independently programmable, and very well integrated computing power available. So why not use that to actually get away from where all the security products are working from and, write some cool code that do funky stuff. Now, is this something that's going to help malware or this? Well, it might. To me, I'm kind of interested in this from a lawful interception perspective and instrumentation perspective. There's a lot of things that can be done, but more than anything else, what I hope to get through to you is that how bad the environment is out there today when it comes to these peripheral computing resources. I mean, it's really a jungle out there because it's highly fragmented, diversified, and everyone does what they think is right. It's not a part of the operating system security model and so on and so forth, but we'll get to that in a second. For the time being, let's look at the GPU so that we cover the bases, right? Okay, so when it comes to GPUs, currently there are 3 mainstream APIs or frameworks to program them with. There's NVIDIA CUDA and ATI/AMD Stream Computing, and then there's Apple OpenCL. Hopefully Apple's OpenCL will win over these things because I think it's much nicer to work with, but who knows? And then, of course, there's Intel Larabi. I didn't really want to mention it because it's been coming for a while. So, just out of curiosity, does anyone program GPUs here, like custom code for GPUs? Okay, we'll run through this really quickly. Okay, on the programmable GPU side of things, generally, you write C-like code that runs on the vector processors on the GPU, and the way it works is that you write the C-like code, and it gets compiled into an intermediate language, which is vendor specific, and then the compiler basically, when you target a device, it basically generates device-specific code for it. I mean, the reason is pretty obvious. Like, GPU vendors want to reserve the right to change their GPU architecture as they see fit. You put an IL in the middle, you have an abstraction layer, you're done. So generally, this device-specific code is embedded into the platform binaries. So when the platform binary is loaded, the GPU code is loaded, verified, and uploaded into the GPU. Now, what are the problems with running code on the GPU? Well, it depends on who's asking, really. I mean, if you're talking about people who write graphics code, well, they have options available to them because they can do source-level debugging either through IL emulation, or alternatively, you can compile in such a fashion that the GPU targeted code is compiled on the host CPU and run on the host CPU with the debugging support. So for graphics programmers, not so much of a problem. But if you're looking at, like, say, for example, a malware analyst who is interested in chasing down the specifics of an algorithm that is being offloaded onto the GPU, well, that's problematic because, well, there's very little. Well, first of all, you don't have source level access. Second of all, what you get is a blob of device-specific code. It's not even IL. And there's virtually no hardware debugging support on the GPU itself. Now, does this mean that all the malware will run on the GPU? Well, no. And there's many reasons for this. And the strongest reason being that even though GPUs pack a lot of punch, they're not as GPU scene would like to be, in the sense that they're not as general purpose as you'd like to be to do some of the more interesting stuff from a mobile code perspective. So, for example, some of the limitations are that no self-modifying code is possible on the GPU, which is not entirely a problem because obviously, you can code your own virtual execution environment and then have self-modifying code. So it's not a huge problem, but all the same, there's no native self-modifying code support. If you really want, I really don't want to focus on the GPU. I just want to sort of talk about it for a bit of background. For additional information, you can refer to this. This is a presentation by Daniel. He's a pretty cool guy. He presented this at RuxCon last year. And it's online at the RuxCon archive, so feel free to have a look. It's pretty good. He goes into a lot more detail about the GPU stuff than I do. But just before we move on, to give you a small example of the kind of stuff that GPU might assist mobile code in, is like, for example, take malware, right? For command and control, for example, a lot of malware uses algorithmically generated domain resources or other communication resources that out of which you would pick one at random and try to connect to it. So one of the best strategies that we have to deal with this is to reverse engineer the algorithm, figure out what these resources are, and then proactively go out and shut down access to these resources. So for example, there's been some high-profile cases of botnets where they were using algorithmically generated domain names that were bulk registered by the bad guys, and they were used on a round-robin or random fashion to communicate as a CNC channel. So what some of the guys did was that they basically reverse engineered the algorithm, generated a list of resources, went back and just disabled all those domains, right? You stop the spreading and control right there. Now imagine a situation where this algorithm will be offloaded to the GPU. I'm not saying the reverse engineering will be impossible, but it'll be a bit more tricky because it's going to take a little long time. A lot of malware analysts don't work with the GPUs. They don't program GPUs. A lot of automated tools that exist for the purpose of analyzing and classifying malware doesn't actually support any GPU, no GPU emulation or nothing. So it can buy people time. It can buy malware writers time. And this is just, the tip of the iceberg. Like, say, for example, if they decided, okay, what we're going to do is we're going to go and implement this algorithm such that it's being used as a cryptographic black box in the unpacking process for the wrapper of the malware, right? So that's even more annoying, especially if they don't unwrap it all at once. So at that point, if you unwrap on demand using the GPU as a cryptographic black box, then it's problematic because you can't just wait for a certain point and dump it all at once. You have to achieve a certain level of coverage throughout the entire binary to ensure that you have enough unencrypted material to deal with. So there are a few things that malware authors can offload to the GPU reasonably successfully that can kind of throw a spanner in the works for us. But there's bigger problems out there. So I'm just going to move on and focus on some of the bigger issues. Okay, so let's get back to our modern computer, right? So in many of these peripheral devices, which contain programmable computational elements, you're beginning to find a lot of general purpose programmable CPUs in there. Like, I was very surprised when Joe was talking about the Gem Plus cards. Like they have an 8051 core. Okay, so You have the Gen+ core functionality, and then you have an 8051 core. Obviously, if you can inject code into it, you can do a lot more because the actual hardware is capable of doing a lot more things. So, when you have custom silicon, like I mentioned before, you're kind of limited by the hardware design. But when you have a general purpose core in there, you're at the mercy of anyone who can inject code into it. I mean, like the rest of the computer is not any different. I mean, the keyboard has had an independent programmable microprocessor in it for a very long time. The only difference was that the standard piece, a standard AT keyboard, didn't actually allow you to do firmware updates. So you were kind of safe there, and it wasn't really dealing with a lot of structured data, so you couldn't really exploit a vulnerability or anything like that. Well, maybe you could, but I didn't know about it, so who knows. So you look at some of the keyboards out there today, like some of the more gaming keyboards which have all the other kinds of functionality, and you look at some of the firmware updates of these things, it's a bit of code out there. So you wonder what kind of functionality these things have. So I'm going to get back to that. So before that, let's look at some of the other stuff. Okay, so we know that your keyboard has a programmable microcontroller, field programmable if you're lucky or unlucky, whichever you look at it. Your optical disk drive definitely has a field programmable general purpose microcontroller in there. So does your hard disk. A fair few of network controllers do too, and a lot of multimedia devices. And even some of the more security sensitive things like there was a field upgradable general purpose CPU in one of the PCI memory acquisition cards that I once looked at. I mean, talk about being owned, right? Okay, not just your PC, I mean, even your phones just have multiple microcontrollers in there. Like, for example, any smartphone today has at least 2 programmable microcontrollers and a DSP. Like, for example, the iPhone, I mean, the poster boy for the smartphone generation, has 2 ARM cores, one in the baseband processor, one's the application processor, and it also has a DSP to do all the media decoding and encoding. So it's a lot of programmable computers out there that kind of share the same resources, completely bypasses the security model because no one cares about it, and field upgradable. So what are some of the security implications of this? Peripheral devices have low-level access to the system, duh. So, they sit on the bus, they do all kinds of funky things, and they handle data, like a keyboard would have access to your keystrokes by definition. Your hard drive controller would have access to your data by definition. So, even though no one considers the integrity of these devices to be crucial to the system security model, they're right there sitting, just passing your data back and forth. So they're very strategically placed. And just like anything else, I mean, all these field upgradable general purpose microcontroller-based peripheral devices are vulnerable to at least 2 attacks without even getting into the hardware level. One is obviously firmware update attacks, where you basically update your own firmware to get it to do things that it's not supposed to do. Or you can have runtime code injection attacks. Just like, it's not any dissimilar from a piece of network software. It runs code, it passes data back and forth, it processes structured data, and it can be owned. And on top of that, put it this way, electrical engineering crowd is not exactly on the cutting edge when it comes to getting security right. So it's pretty mad. So let's take a quick look at one of the firmware update attack examples. This is obviously in the public domain. You guys can go and have a look at it in detail if you like to, because you could probably spend 2 hours explaining how it was done. It's very cool. Basically what they're doing was they basically reverse engineered one of the Apple firmware updates for the Apple aluminum keyboard. They embedded their own code into the firmware update and implemented a rudimentary keyboard sniffer right on the keyboard. So there you go. I mean, you're, well, I mean, pardon me for my French, but your security product can kiss my ass, right? I mean, your anti-sniffer stuff can, well, do whatever, it doesn't help. And you can throw your little key sniffer dongle away. I'm not accusing you guys of using such a thing. I'm just saying you can just throw it away. So yeah, that's the title of the presentation. You can find it in the Black Hat archives. It's really cool. Check it out. Okay, any questions so far? Yes? No? Maybe? No? Okay, this time I'm going to take the silence as a no. Okay, runtime code injection examples. Let's take the poster boy of our smartphone generation, the iPhone. Okay, how many people have iPhones here? Okay, how many people have unlocked iPhones here? Okay, the iPhone unlock is quite interesting. The network lock is implemented in the baseband processor, which takes care of the network communication side of it, or their network communication side of it. So, interesting things. The baseband code firmware is encrypted, and it's actually pretty hard to update the firmware. But interestingly enough, the interface between the baseband processor and the application processor, which is implemented very much like Android, very much like Nokia BB5, that interface is vulnerable to simple Stack Overflow attacks. And the particular vulnerability that works for the baseband that came with 3.0.1 is called the 80 plus xlog equals 1 blah blah vulnerability. It's a straightforward Stack Overflow, so you don't need to overwrite firmware at all. You can basically inject code, and once you inject code, you can do whatever you want with it. So you don't really need to have the ability to be able to overwrite firmware to be able to exploit these devices. If they have a vulnerability, just like any other piece of software, you can exploit them. And the iPhone wiki has some disassemblies of the actual ultrasnow code. They have brief description of the vulnerability as well. And obviously, you can download it from CDR and you can have a look at the code yourself. I think you might be just breaking the end-user license agreement on this, but not that I would encourage that sort of thing, obviously. Okay. So now that you guys have a quick, rough idea of what the kind of things that could be done, let's take a quick look at the evolution of malware so far in terms of the motivations. So, I mean, obviously it's no secret at this point that there's money in malware, right? I mean, malware has been industrialized, so to speak. So there's a lot of infrastructure built for malware. There's like a lot of specialization in the malware sphere. I mean, there are guys who write libraries for malware, libraries for rootkits, so on and so forth. And because of this commodity code base, it's constantly increasing in sophistication. So malware is going places. And I mean, sure, the security products are trying to catch up. They are catching up, not catching up, trying to catch up, the traditional cat and mouse thing. And it is not very difficult to imagine that sooner or later, my guess would be sooner, that they would wise up to some of these things and start messing around with some of the opportunities offered to malware authors by a lot of these peripheral devices. Now, one of the key things about the malware problem, particularly, is that these days, unless it's a targeted attack, for a lot of malware, 100% exploitability is not a requirement. So keep that in mind, because we will come back to that. That's a bit of a crucial feature in this battle, because you will see later on that it's a problem for the security community, but not necessarily for the malware writers. Okay, so targeted attacks are getting more prevalent, and targeted attacks are getting actually very, very sophisticated as well. So it is not inconceivable that they will be moving into this type of thing on a more massive scale in the years to come, unless we wise up now and clean up some of the mess that's been left behind all these years. Okay, so from the malware perspective, why would you want to run code on peripheral processors? Well, the threats are not mainstream, so security companies don't deal with it, care about it, have infrastructure to address it. It's a massively diverse device space out there. Everyone does their things the own way. There's no standardization whatsoever. So it's a problem for security vendors because they have to go out and research, maintain the skill base, build technology to deal with, and support a massive number of devices that are out there. And at the same time, there is no OS infrastructure to do that either. Like there is no standard OS model to do integrity and security verification of devices. There's not even a standard OS model to maintain some of those firmware updates for these devices. I mean, it's just as bad as the software security update situation. Everyone does their own thing, but it's a little worse because if you have a piece of software that is not privileged, you can update to do whatever you want to, but you're kind of stuck within that privilege boundary, within that security domain. But when it comes to hardware that has so much access, specifically some type of hardware, like you're asking for trouble, right? So, like for example, if you were to look at, like when I was talking about this to someone else before, they mentioned that when we move to virtualization, when a lot of things move to virtualization, this is not going to be a problem. Well, yes, if you're dealing with virtual devices, this is not going to be a problem, right? But obviously, then we are going to face with the problem of the virtual device implementations. But I mean, that's a different ballgame. But if you're looking at where things are heading, where we are going into IOMMU architectures and getting into virtualized devices and pass transactions directly to them, you still have this problem. If you, like on the iPhone, if you manage to get a legitimate request out to a device that you know it's going to process, like say for example, running some type of GPU code, or some type of like getting the sound card to do something silly that it's kind of sort of supposed to do, but not in the same way, you still reach the hardware device. I mean, it goes through multiple layers, but you ultimately have to hit the hardware device. So there's still opportunity to own this hardware, just like with the iPhone baseband. You can potentially still do direct runtime code injection. So you might say that only the hypervisor or high security domains will be able to update the firmware on it, which is fine, but you still have runtime code injection problems. So virtualization doesn't actually solve the problem. It kind of mitigates it a little bit, but not really. So look at malware analysts. I mean, malware analysts are largely dealing with x86 code. They have all the infrastructure. They have the knowledge base that was built up for 20 odd years. They have all the software. I mean, not to say that we're all on top of things. I mean, there's still some challenging stuff out there, but this is a whole heap of new problems because, I mean, okay, how many people here have actually worked with an MELPS 740? It's a core from Mitsubishi, I believe, and Renesas uses it too. And well, probably you guys, some of you guys might have worked on the ARM because ARMs are quite prevalent on the smartphone side of things. But yeah, there's like so many processor architectures used in these microcontrollers. So imagine from a security vendor perspective, suddenly if I had to maintain a knowledge base and invest in infrastructure, deal with all these security architectures, if you get enough volume, it'll probably be worse than the signature bloat problem that we are trying to deal with today. And the other thing is a lot of these devices are undocumented. I don't know how many of you were here for Joe's talk in the morning, but one of the things that Joe was saying was that a lot of these devices are built around reference designs. And yes, that is true. So you can learn a lot of information from these reference designs and other side channels. But there are a lot of other classes of devices out there. For various reasons, they wouldn't even give you access to a reference design or any literature other than the basic data sheet for contractual and license reasons. For example, optical disk controllers. DVD CCA do not want you to mess with low-level chipsets that deal with optical drives. You will not get a vendor to return your call. You will not get an SDK. If you're lucky, they won't sue you. I mean, DVD CCA is mad about these things, so like there's classes of hardware out there that you can't even get a reference design for. You can't even find some of the chipset numbers and the identifications on the web. So a lot of these things are largely undocumented. And when it comes to runtime debugging for analysis purposes, we have some pretty cool stuff on the CPU side of things, but on all these peripheral devices, we are kind of like, I think the technical expression is SOL. I'm not going to spell out what it is. You can kind of like, I mean, if you are particularly sophisticated, you can kind of get around some of these things. Like, like some of the stuff that Joe is doing, hook it up, see if there's LPC port or a JTAG port that is still enabled. Try to get some code injection happening so you can wire up a rudimentary debugger in there. So there are things that can be done, but it's not going to be like loading it up in IDA or running it through Metasm to clean it up and just loading it up in IDA or whatever. So it's going to take a bit more work to just get to the level where you can deal with some of this stuff. I mean, for a lot of these devices, you get like a blob and you don't even know what instruction set it is. You don't know where it's mapped in memory. You don't know what the register spaces are. You don't know how the memory address space is partitioned. So it takes a lot of prep work to get to the point where you can analyze some of this stuff. So why shouldn't malcode run on these things? For exact same reasons. But I mean, obviously, the defensive and offensive side is different, right? I mean, I have a friend who always says that offense is pure. Well, it is true. It is narrow and deep, whereas defense has to be wide and hopefully deep. I mean, it's not going to happen, but it has to be wide and deep. So for someone who is interested in writing malcode, like especially in a targeted scenario, say, for example, company X buys all their computers from Dell. Their latest batch was like 100,000 computers or how many amount of the same model, because IT likes to keep things simple. So there's this whole lot of homogeneous hardware out there, and you can just focus on one of the interesting devices in there, spend your time on it. There you go. You got 1 in 100,000 chances of just getting it in there, if you're lucky. So for malware writers, the game is a little bit different. So they have the ability to bite down and just spend a bit more time on these things. Okay, so does everyone agree that it's kind of bad out there? Okay, so I will go and discuss an actual example and walk through some of the things that have some of the development process and what can be done with it. But before that, let's figure out, let's see, I mean, how can we potentially sort out this mess? What can we potentially do? I mean, like, who do we have to visit with a baseball bat, right? So, or a check. I mean, either way. Sometimes a check might make a bit better. Okay, device manufacturers, obviously. Computer vendors, operating system vendors, security and system management software vendors. Especially in the enterprise, it's not a trivial process of just walking there and just taking inventory of what's on every computer and making sure that everything is up to date. So we need all these guys to play ball to kind of like work through this stuff. Device manufacturers, okay. Probably most of my gripes are directed towards them. For crying out loud, this is 2009. Stick to a strong SDL or any SDL. I mean, we talk about how a secure development lifecycle is important for OS vendors and application software vendors. What about hardware manufacturers? What about device manufacturers? First of all, verify your hardware. Ensure that it can only do what it's meant to do. Audit your firmware and drivers. There's a reason for this. I will focus on that a bit later. convince your chipset manufacturers, your operating system, your real-time operating system manufacturers, your SDK and library vendors, or even sometimes the compiler vendors, to at least audit their code from time to time if they can't stick to a proper SDL. And why is this important? For the same reason that Joe mentioned, Joe was talking about when it comes to the reference designs. When you buy a chipset these days to build your hardware around, what you get is the chipset, a reference design, and an SDK, and sometimes even a compiler and supporting libraries. So you write your specific features on top of it. You don't even touch what's underneath. And quite honestly, there's a lot of device manufacturers and people that I've spoken to who write firmware for a living who had no idea of the capabilities of the underlying chipset. I mean, at the time, it was great for me because I was actually getting the chipset to do things that it was never meant to do. But yeah, it was baffling as to what percentage of people I spoke to out there didn't really even understand the hardware. They were given an SDK, they were given the documentation, so they treated the SDK like the actual representation of the hardware. But obviously, it was not an exact one-to-one mapping. Often the chipsets are a lot more capable than the SDK would expose. So it's extremely important to have all these guys play ball and audit their stuff, because sometimes the device manufacturer might not even know why they got owned. Focus developer attention to security when producing code. I mean, this goes without saying for the entire industry, but especially in electrical engineering and device manufacturing, that type of thing, they're under a lot of different types of pressures. They want to get the device out in least amount of time, and not often do people come and complain. It's not like the White House is going to give them a call and say, hey, you got a problem with your UPnP. It doesn't happen very often. So they've gotten this situation where they err on the side of convenience as opposed to security. So that really needs to change. And also the developers have to be educated about the greater security model in which the device operates. I mean, this goes without saying with driver writers too. I mean, I don't know if you guys have noticed it, but there are many class drivers in Windows which implements a certain security model for their devices so that it doesn't actually break the OS security or attempt to break the OS security. And then there's a low-level transport driver writer who doesn't go and set any ACL on their driver. So anybody and their dog can actually send device I/O controls to it. So these device manufacturers and developers need to understand the greater security model in which they operate. Device developers, do it yourself. Don't trust the driver. Don't expect, firstly, that the driver you're talking to is the driver written by your guys. And secondly, don't expect the driver to pass things that it's only meant to pass. Same goes for device driver writers. Don't trust devices to return valid data or responses. I mean, there are many faulty drivers out there that can be exploited by devices that are masquerading to be the device those drivers are intended for, but not. So, I mean, ring zero injection by just plugging something in your USB, not so good. Okay, so in general, distrust and do-it-yourself is really great for security, because just because you're paranoid doesn't mean they're not out to get you. Now, hardware shouldn't really trust firmware either, but to me that's less of a problem. I mean, that might be a problem for the DVD CCA, but it's not, to me, it's not so much of a problem. But realistically speaking, hardware shouldn't trust their firmware too much either. The hardware should ensure that the firmware is not trying to do things that it's not meant to do. Now, moving beyond just the low-level things, don't expect anyone to adhere to the protocol or the standard that you've implemented, because the chances are there's going to be some troublemaker somewhere sending it stuff that's not supposed to. when you're auditing code, especially pay close attention to the parts of code that get tainted by I/O, especially that can be controlled by the user. So, host device communication handlers, structured data passing, any kind of complex user data processing. These things can be problematic. I mean, this is not, when you're talking about devices that have multiple interfaces, it's even a bigger problem. Like, for example, if you take a phone baseband, they can't trust the OTA, which is the over-the-air interface. And they can't quite trust the application processor either. They've got to watch their own back. And surprisingly enough, for the iPhone owners out there, we are very lucky that the GSM frames are so short. Let's just leave it at that. Okay. So what do we want the device manufacturers to implement? We want them to implement a secure, it's all about risk management, so an acceptably secure firmware update process. And packing your update with UPX or running TEA on it doesn't quite count, unfortunately. Use decent crypto. It's available. It's out there. This is 2009. Also, one other note, downgrading firmware can make sense in certain circumstances, but it's generally not a good thing. So be aware of that. I mean, e-fuses are there for a reason. If you don't know how to use it, go ask Sony, they'll tell you. And also, implement a firmware verification and validation process for runtime. This is important because you need to be able to, at any given point in time, from a security perspective, you need to be able to ensure that your devices are operating within their specifications, i.e. that they haven't been tainted or not functioning as they're supposed to. So it's important to have this runtime verification process. It must be resilient against manipulation by rogue firmware. So you can't basically tell the firmware, hey, read all your memory and give it back to me so I can just do a checksum and see if it's okay. Because if the firmware is owned, I'm pretty sure that it won't give you exactly the bytecode that they've injected. Don't get the firmware to validate its own integrity. I mean, it's just as bad as the parking meter asking the smart card how much money you got. Also, it is extremely important to, whatever methodology that you implement, it is very important to open this up to other security players, like, computer vendors have a vested interest in this. The operating system has a vested interest in this. Security and systems management software has vested interest in this. So they need to be able to have visibility into whatever this integrity mechanism that you implement. Because if it's only been done through your program, it's generally no good, because most likely no one will end up using it, except the extremely paranoid, of course. So in a perfect world, device manufacturers will be open about their security updates, tell people what they exactly did and why they changed the firmware and why they should upgrade. Have some kind of back and forth information channel open so that other players can actually get an idea of what's going on in a consistent fashion. So key point of any successful relationship, communication. Well, actually, maybe it was fear, but anyway, we'll stick to communication. Okay, now what can computer vendors do? Well, firstly, coordinate with the device vendors to have prompt upgrades. In many cases, you find your OEMs who are using devices from various manufacturers, right? Like, say, Dell or HP or whoever. They obviously don't manufacture all the devices. I mean, they do provide you firmware updates, but not as frequently or as promptly as some of the device manufacturers would. Not to say that the device manufacturers are doing a great job. When it comes to the computer vendors, it's even worse. There's a massive lag in between there. And also, coordinate with device vendors and give people the ability to maintain security and integrity for your devices. Like for example, when you get a computer from the factory, well, maybe you can assume that the operating system image is safe, which is not exactly a problem, because like in many enterprises, you will basically put a standardized operating system environment on top of it anyway. Well, obviously at that point, you had to trust the guy who made the SOE image, but you got to live with it. But when it comes to operating system side of stuff, I mean, it's kind of taken care of. There's a lot of security products out there that can give you a reasonable level of assurance there. But when it comes to the actual firmware on the devices, there's nothing there's absolutely nothing that you can do, because you wouldn't even have a tool to verify this actually has the firmware it's supposed to have. So, I mean, this is obviously a problem. So, like, sometimes you can go to the vendor and just basically download the latest firmware and update it yourself. But if the firmware isn't really updated and you have the latest firmware version or the release firmware version, they won't usually give the update to you, because that was for the product shipped with. So even then, you have to use these gazillion programs to just go out there and do all these things, which is horrible. So work with these guys and get something in there so that you can have this standard framework, or at least uniform framework, where you can at least ensure that your devices are running code that is only meant to, from a firmware update perspective. OS vendors, coordinate with device vendors, computer vendors, get something going there. Please extend the security and device integrity into the system security model. If you have a device that can do nasty stuff, it doesn't matter what security you put on top of it. If the device is owned, the device can manipulate, modify, sniff data. So it's an important part of the greater operating system security model. So please, let's start considering this. Security and systems software, the OS should really provide them a framework to deal with these things. I mean, you can't realistically be expected them to go and invent everything, because there's a chance that Microsoft or one of the OS vendors will at some point go and change it anyway. So, okay. I think I need to really quickly move on, because it's going to take a while longer than I expected. Okay. If you guys are working in security ISVs or system management software ISVs, please lobby the device guys, lobby the computer guys, lobby the OS guys to take these things seriously, and also please, once you get to a point where you can implement some of these things, give some greater visibility to the admin so that they can have some idea of where they're at. Okay, to finish off, I'm going to walk you through an example of how bad these things could really be. And hopefully it'll motivate you guys to kind of have a look at it and take this seriously and do more research in this area. Okay, so the idea of this is to just illustrate one example of what could be done with exploiting peripheral devices. Okay, so let's say there's a peripheral device X, and so we want to exploit device X. What do? We basically see if there's a firmware update mechanism. Is there a firmware update? Luckily enough, we can find it in the vendor support side. Cool, we get the updater. Before we get to what the update is, what we're going to do with this, let's take one step back. Who actually works with developing custom PCI devices out here? Okay. Basically, there's a mode of many buses called bus mastering DMA. It exists so that the device can directly talk to and transfer memory between another peripheral device on the same bus, or more often than not, with the main system RAM. And PCI bus implements this function. There's a lot of devices that implement this function, so you don't need the CPU to program a DMA transfer in there. The device can initiate a DMA transfer by itself. I don't know if you guys are familiar with the FireWire stuff, where you could do a device initiate DMA transfer. So the FireWire specification allowed it, but the actual chipset, at the chipset level, the FireWire chipset sitting on the PCI bus would do the same thing. So, So to give you an idea of what type of devices use bus mastering DMA, a lot of high throughput devices that need quick access and to move a lot of volumes of data end up using bus mastering because they want to maintain minimum CPU utilization while doing all these things. So I'm sure you can all guess like, what kind of device out there that does bus mastering. So what do we do with this bus mastering device? Well, you have the ability for this device to initiate DMA transfers to and from main memory. Then you have a general purpose programmable microcontroller on it. So what you get if you can actually inject code and get it to initiate DMA transfers, you get the ability to basically read or write anywhere in system memory, in the RAM. And the RAM factor is quite interesting because when you're writing to RAM, basically none of the MMU features that are meant to protect you from a privilege level scenario applies to you because you're writing directly to the RAM. If the RAM is paging, you can write to it or read from it. So let's take a look at this particular updater. It was packed with ASPAC, and it had encrypted firmware included as a binary resource. Basically, there was part of the code where the binary was actually reading the encrypted blob, processing it, and then uploading it to the device. So this part was actually quite garbled. So obviously, someone thought that we really don't want people to look into this. So on top of the ASPAC, they actually garbled something, and I'm pretty sure that they had done this like this existed from like their DOS update or whatever. It looked like pretty old-looking code. So what do we do in this situation? I personally use Dynamics BinNavi, which actually provides very good scripting functionality. And I quickly wrote a script to basically do the same kind of thing some of the Medasm guys were doing. And I'm removing some of the garbage code. So once you do that, you can clearly see how the firmware update process works. And then what you do is you just take the firmware prior to being processed and uploaded to the device in its unencrypted form. Then you need to identify the instruction set. Sometimes easy, sometimes hard. You've got to identify the target device. Sometimes easy, sometimes hard. Once you kind of have a basic idea of what the instruction set is and where it may reside in memory, you can load it into IDER. You can do additional research, refine the memory map, figure out where things stand, analyze the key functions, figure out what everything is doing, name them, add commands, and something that is particularly important for the kind of thing that we're looking at is that if you know what type of commands that the device accepts at the bus level, that's very helpful. And there are many devices out there that actually have standardized command sets on top of vendor-specific ones. So those standardized command sets is a good place to start, like various MMCs, for example. And there might be some holes that you want to deal with that in your understanding to get where you want to get. So some of the things that I found useful is to compare different versions of the firmware and check against, cross-verify against bug fix information to figure out what they fixed, and then identify the portion of code that has changed. So you kind of know that this is where it might have been fixed. Sometimes it's easy because the code has changed only a little bit. Sometimes it's a bit harder. But generally, that helps a lot. Also, if you have different related devices, like if you know that the same chipset is used by multiple manufacturers in different devices, it kind of helps to get all the firmware and have a look at all of these things. Because some of the manufacturers implement features differently. Some enable certain features of the chipset while the others don't. So you can look at what code changed these things, and you can clearly see, like, okay, this is the code pertaining to that particular feature. And something that I really find helpful for this is a tool like BinDiff, because you can port your names and comments and so on and so forth. So it saves you a lot of time, and it gives you a baseline to work with as well. It's quite quick. When you're doing these things, you can also look for strings, shared library type situations, where you can find the RTOS code, the SDKs that they're using, their compiler artifacts. So there's a lot of stuff out there that can kind of help you orient yourself and understand what's going on in there. But ultimately, your goal is to understand the bus command handling, responding, and how to set up bus master and DMA transfers. And once you do that, well, just embed your injection code and you're ready to go. So write code and just write code into the firmware, update the device, pray that it works because I've bricked more devices than I would like to think about. Sometimes it helps to just return it, like, or, well, I kind of played with it, but it doesn't work anymore. And it sometimes works. In one particular case that apparently it was sent to the manufacturer and they returned it, saying that the firmware has been maliciously manipulated. So sometimes, it doesn't quite work out. In general, for anyone playing with firmware or embedding stuff into firmware, I highly advise as a first exercise, if possible at all, to write a small piece of code that allows you to inject code on a regular basis and just try it out to see, because writing into the firmware and screwing it up is an expensive process. So install a custom command handler that takes your code as input and executes it and establish a channel to get the data back. I mean, for storage devices, for example, fairly easy storage, that's what they do, pass data back and forth. So alternatively, I've also lately spent more time on actually looking for vulnerabilities in these devices. And if you find a supporting processor architecture, Binder is very useful. Unfortunately, at the moment, it doesn't support a lot of processor architectures, but for the ones that they support, it's quite useful. Because more often than not, you'll realize that, hey, hang on a minute, I don't need to implement anything. There's this nice bug waiting for me to just inject code. So in this particular case, what do we want this modified firmware or injected code to do? Well, okay, this device sits there serving legitimate requests. So what we want to do is that we want this device to do something after we are reasonably sure that the rest of the operating system is initialized. Okay, so what do? Well, we put in a firmware and say, okay, after n number of reasonable requests upon initialization, do something. So what is this something? Well, for example, write a bunch of data to the none-page pool in the kernel. And if you pick the right place, you can be reasonably guaranteed that the pool won't be full or you're overwriting something important. But I mean, this is kernel exploitation 101. There's many ways around it. There's many ways to reliably do this. I mean, obviously, you don't have to do this. If you know certain like magic flags in the kernel image that would be helpful if you just happen to flip it or something like that, you can do it. It's a bit tricky because the transfers are not exactly byte granular, but you can get around it. Achieve payload execution, very much like kernel exploitation 101 again. Basically, I mean, that's about it. So once you get the device to inject the payload into the system RAM at a certain point in time, transfer execution control to the payload, and once the payload is done, the payload can let the device know that it's completed through the custom command, again, that you've implemented. And it can also specify which payload to run again and at what point to run it. So at that point, you're comprehensively well and truly owned with your device. So what are some of the advantages of this? The payload exists in the system memory for a very short period of time. So even if you're taking system memory dumps from time to time, you have to time it right to just make sure to see this code, to see the payload, to just get it at the right time. And then everyone will have, like the guy who is the incident response guy who's looking at it will have to figure out how this code got there. And even when it exists in the system, if you use multiple payloads or other mitigation factors, you basically only see a very small portion of the code, which may not make a lot of sense. So again, there's a layer of difficulty there. And well, my favorite is that it actually survives reboots, of course, without writing anything to the file system. And it survives OS reinstallations. So that's kind of funky. And if you write your payload in a reasonable fashion, which I haven't done, but theoretically, there's nothing saying that you can't write a certain type of payload that would affect any OS that you plug the device into. So it's possible. Like I said, yeah, you take the device, you attach it to another computer, like bam, gone. So, so yeah, I mean, if you happen to be in intelligence and you want to sort of get into a certain office in the middle of the night, and just rather than swapping the entire computer, you can just swap a device and just walk away. Okay, questions? Sorry for taking about 4 minutes over and rushing through the end of it, but any questions? No? Okay, time to go and drink then. Yeah, if you guys have any other questions, actually, hang on one more second, I forgot something. Right, if anyone can figure what this one is, what this is, or at least what CPU architecture that is, I will tell you what device it is. Any takers? I mean, really, like, you look at this and it's, I mean, there's a bit in there. I reckon at least you could try to figure out what class of device this is.